Okay, so let's go ahead and get started with the solutions to homework number 5. So there are two homework 5s, and this is the one that was due on 2/21/2020. So this one was the actual homework 5. The next one should have been homework 6, but was still labeled as homework 5. Okay, so question 1 says an open box is to contain a volume of 3 meters cubed. So question 1, we have a box and the volume of this cube is 3 meters cubed. Given that the material for the sides of the box costs 6 whatever per square meter, um, I'll say dollars per square meter, and the material for the bottom is 9 per square meter. Express the total cost C of the box as a function of the length and the width. So let's call this the length, and this is the width, and this will be the height. Right, an open box. Yeah, okay. And this is the height. Okay, so real quick, what do we know? We know that volume is equal to width times length times height. So, and then what is the area of all of the sides? So, area of the sides, that's going to be, so we have the length times height side, we have 2 of those, plus 2 of these ones where we have the width as the base and the height as that, like this. Okay, so and then the area of the bottom is just going to be width times length. And it says an open box, so that means there's no top. Okay, so here with this one, I can rearrange this, and I have H is equal to V over WL. And why would I want to do this? Because I know that V is just always 3. So with H being 3 over WL, I can plug that in to here, and I have area of the sides is going to be 2L times 3 over WL plus 2W times 3 over WL. The L's cancel, W's cancel, and I get 6 over W plus 6 over L. And I know that's the total surface area of the sides. And I know that the cost per side is 6, or per square meter on the sides is 6. So the cost of the sides is just going to be 6 times this. Okay, and then the cost for the bottom, that's going to be 9 times the area of the bottom, which is just WL. Okay, so now I can write the total cost as being I'll just write this as 36 over W, but 36 over L plus 9WL. And that's all it wanted us to find, was just the cost in terms of W and L. Oops, I have more than one page now. Okay, next question. It says consider the level surfaces of f of x, y, z, which is x squared plus 2x plus y squared plus 6y plus 20 minus z squared. So the level surfaces are the sets that we get of all values where this is equal to some constant. Um, okay, it says for what values of C is the surface with the equation um, f of x, y. So we're looking at the level surfaces like this, and it wants to know when is this a hyperboloid of one sheet, and when is it a hyperboloid of two sheets? Um, okay, so I will explain what the one and two sheets are here in a second, but let's go ahead and just look at this. So um, yeah, so this, I'm going to go ahead and just factor this so I can uh, work with it a little bit easier. So this is going to be um, f is x squared plus 2x plus 1/2 that squared is 1 plus y squared plus 6y plus 9 um, minus z squared plus 20 minus 1 minus 9. So which can be factored as x plus 1 squared plus y plus 3 squared minus z squared um, plus 10. Okay, so if I have f of xyz equals c, so I set this equal to c, then what do I get? I have x plus 1 squared plus y plus 3 squared minus z squared equals c minus 10. Okay, so real quick, a hyperboloid, um, so this is kind of hard to draw in 3D, but if we imagine we're looking at this surface from the side, okay, so this is going to be up, and this will be y or possibly x. I won't be able to see the x-axis coming like straight out at me. Um, this is going to look like one of two things. It's either going to look like this, right, and be kind of like two bowl-looking things going at each other, or it could possibly also look like this, where they actually connect. So in this case, we kind of have two separate sections. We have two sheets. And here we have just one sheet, one surface. So this is what it's asking. When is it one surface and when is it two surfaces? So the easiest way to do this is figure out for what values of C does this not intersect the x-axis or the xy plane. So what is the xy plane? That's the plane where z equals 0. So if z equals 0, then we have x plus 1 squared plus y plus 3 squared. Z is 0, so this is c minus 10. So notice no solutions when c is less than 10. Right, if c is less than 10, then this has no solutions. There's no x and y points with z equals 0, meaning that these curves don't intersect this axis. They don't touch the xy plane when z is 0. Right, the surface isn't defined there. So this is going to be the two sheets. So when c is less than 10, uh, oops. So, and just to recap again, how do I know that I have two sheets? Because I can kind of separate them with this plane, the xy plane. So, that's when I have two sheets. So if um, C is greater than or equal to 0, right? If it's greater than or equal to 0, we're going to have this case where it's all one sheet. Okay, next question. So it gives us the function f of x, y equals x cubed over x squared plus y squared. It says determine if this has a limit as xy goes to 0, 0. So to do this, I need to either prove that it goes to 0 in any direction, or I need to prove or find a counterexample, right? Find two different directions where I get something different. Okay. So if this is 0 and 1, 0, 1. Okay, so here, if I do the limit with x goes to 0 and y is fixed at 0. So I'm going to check a couple of things first, just to see what this looks like. Okay, so if I do this limit, x cubed over x squared plus y squared, what happens? So I get x cubed over x squared, right, because y is 0. This is just x, and that goes to 0. So the limit is going to be 0. So that corresponds to the limit, let's see, so y is 0, when I'm going in this direction or possibly this direction, depending on if x is positive or negative. But that doesn't really matter. So now let's try going in along the y-axis. So here we have 0 over 0. Okay, yes. So here, we check a couple of things, and it looks like um, at first glance, this limit is also 0. So at first glance, we see that they all go to 0. And this kind of gives me an idea that this is what I should be trying to prove. Right? It's not like super easy to construct a case where I have different limits. Also, notice on the bottom we kind of have stuff to the power of 2, and on top we have stuff to the power of 3. So if you remember from examples from Cal 1, um, we were kind of able to just like cancel out the exponents and say this is basically like x, so this goes to 0. So we have to be more careful here, but this gives me an idea that this does actually go to 0, and this is what I should be trying to prove. I also needed a guess on what the actual limit was. Okay, so what I'm going to do is I'm going to look at the difference between um, x cubed over x squared plus y squared. I'm going to look at this difference, right? How far away is this value from 0? Okay, and I want to show that the limit of this expression goes to 0. So I'm looking at the limit of this, and what I want to show is that this goes to 0. So the first thing that I notice is that I have x cubed over x squared plus y squared, and I know that on this side it's bigger than or equal to 0. But what else do I know? Let's see, I know that x squared is less than x squared plus y squared, or less than or equal to. So that tells me that 1 over x squared is bigger than or equal to 1 over x squared plus y squared. So this tells me that this is less than or equal to x cubed over x squared. Those cancel and I get absolute value of x. And again, I'm still doing the limit as xy goes to 0, 0. So if I do this limit, this goes to 0. This is bigger than 0, which means that this thing I'm interested in is squished between 0 and 0, meaning it's also going to have to be 0. So the limit as xy goes to 0, 0 of my function minus my assumed limit. So notice if I want to do this, I have to have a guess about what the limit is to start with. This difference goes to 0, meaning that limit xy goes to 0, 0 of this function is equal to that limit. So this is by the squeeze theorem, right? Because this term gets squeezed between 0 and 0, so it also has to be 0. Squeeze? Yeah. Okay. Um, yeah, so just to recap, I'm looking at this to get a general idea. Do I expect that this top dominates or it goes to 0, or what do I expect? I can look at the powers for that, but that doesn't tell me any guess about what the actual limit is or whether or not it actually converges. And then I can do a couple easy checks to see, again, what do I expect the limit actually is. um, because it doesn't matter which one I take, they're supposed to all be the same, and if they're not the same, then the limit doesn't exist. Okay, number 4 says determine whether the function f of xy, which is x over x squared plus y squared, has limit as xy goes to 0, 0. Okay, so in this case, I expect, so here we have a first order on top and a second order on bottom. So I expect that the bottom goes to 0 faster, meaning that this would blow up to infinity or the limit wouldn't exist. So that's just a first guess. Now let's try doing a couple limits. Okay. So I don't expect that this is going to converge. I don't expect that it has a limit. So that's what I'm trying to find. Now I'm trying to find two examples where the limits are different. Um, let's do the same thing we did last time where we fix y as being 0 and then go to 0, 0. So this is x and 0. So that's the limit x0 goes to 0, 0. So x is x over x squared plus 0, which is the limit as x goes to 0 of 1 over x, which first off does not exist. Okay, so that's we're basically done right there. But let me just show you that actually if we do this with y instead of x fixed at 0, what we get is something different. So this is the limit as, so we're plugging 0 in for x and we're just letting y go to 0. So we have 0 over 0 plus y squared, which is just 0. So in this direction, the limit is going to be 0. But in this direction, it'll be plus infinity. In this direction, it'll be minus infinity. But it's all at the same point, right? So we get different values for the limit. So we say that limit does not exist. And actually, so why does this limit not exist? Because from this side we get positive infinity, from this side we get negative infinity. Again, we get two different limits. Okay. Number 5. We're given the function f of xy, which is sine of x sine h of y. And first it wants us to calculate the partial with respect to x. So that's going to be derivative of sine is cosine, and this is just a constant. Next it says calculate fy. So sine, that doesn't change. Derivative of sine h, that's cosine h, hyperbolic cosine. The second derivative with respect to x, which is, so that's the x derivative of this second one right here. So derivative of cosine is negative sine. This hasn't changed. It's just a constant with respect to x. And then finally it says compute fxx plus fyy. So I'm just going to copy this down, minus sine of x sine h of y. And now I need to do the partial with respect to y of the partial with respect to y. So that's going to be that doesn't change sign, sine of x um, sine h of y. These cancel out, and I get 0. And those are my answers. Okay, so next, it says f of xy, so this is number 6, is equal to tan inverse of y over x. So real quick, if we were doing polar coordinates, this would be the angle um, of x and y, right? So here, if this is xy, this f is just giving me the angle right here. Okay, but it wants the gradient of this. So gradient of f, that's going to be the partial of f with respect to x and the partial of f with respect to y. So let me compute these separately. df dx, which is 1 over 1 plus whatever's inside squared. I have y over x. So I need to multiply by the derivative of what's on the inside. So that's times derivative of 1 over x is negative uh, y over x squared. So I can simplify this a little bit. I put this over a common denominator, and I have um, x squared plus x squared plus y squared times minus y over x squared. Those cancel, and I get minus y over x squared plus y squared. Okay. Now with respect to y. So this is going to be the same thing. 1 plus whatever I have squared, so this is y over x. Now I do the derivative of what's on the inside, chain rule, with respect to y. So that's just going to be times 1 over x. So I do the same thing, I put it over a common denominator, and I get x squared over 1 plus, x squared plus y squared times 1 over x, which gives me, let's see, that cancels with one of those, and I just have x over x squared plus y squared. Okay, and this is the gradient. So just out of curiosity real quick, actually, hold on, this isn't the gradient. I need to put this as a vector. So I have minus y over x squared plus y squared, and I have x over x squared plus y squared. This is the gradient of f. And that's my answer. Yeah, I'll go ahead and leave it there. All right, and that was all of homework 5.